Okay, so far we've introduced the har scaling functions. We're going to start introducing a little bit more nomenclature and vocabulary. So we've come up with these v, j, comma, n functions. I'll call them scaling functions. And we have defined a set of spaces that approximate a signal. So we have some very limited set of signals, v naught, that we can approximate using v naught, comma, n. We can approximate everything in v naught plus other signals in v1, and the space v2 includes everything in v1 and v naught, as well as a new set of functions that are a little bit finer. And you can maybe see where this is going. I could go on for a very long time and keep adding more and more outer shells, if you will, so that when we're all done, we eventually come to Vj and all the way up to the infinity, which is all functions in L2 are. Okay, so I'm hoping this visualization is going to help in just a moment, because what we're now going to focus on is the difference between what's in each of these spaces. And we prefigured that a little bit as we were talking earlier. So we can talk about the har wavelets, and we'll get to other wavelets in a bit. But the har wavelets represent the differences between the approximations in Vj and Vj minus 1. Okay, so we're going to introduce now a new function, and it's supposed to be this big script w. I'll see how well I can do a script w. Not too bad, but I have the feeling that it's going to look different every time I do it. We'll try out now. That one's not too bad either. Okay, so v2. Okay, so these are the wavelets, and if we look over at the space at the right, I'm going to color code these the same. So the space spanned by w naught is that space in yellow, and that spanned by w1, there is the space in green. All right, so let's put this together. In essence, this w naught space is kind of strange. So they're constant. Here w naught are constant over intervals of length 1/2. But, and here's the interesting part, because they don't include v naught, so they are orthogonal to everything in V naught. What does this essentially mean? This means that signals in V naught, or I'm sorry, in W naught must be zero mean between integers. So let's look at what that would look like. It's kind of an interesting function. So if this is from 0 to 1, this would be our v 0, 0 of t. What would be an orthonormal function that is orthogonal to that and piecewise constant over an interval of 1/2? Well, that would look like this. Do it in red. Oops. A little bit of operator error here. Something like that. Okay, it's not perfect, but this now ranges down to -1, and we're going to call this function psi t is equal to 1 from 0 up to 1/2, -1 from 1/2 to 1, and 0 otherwise. So this function here, as you can see, it's orthogonal to the phi function, and our psi 0 comma n t forms an orthobasis for W naught. And just in general, then we can define the scaled version of this the same way we did with our phi functions. 2j over 2 phi naught 2j t minus n. And so this is orthobasis for J. That is, actually, I guess I should be a little bit more specific. The orthobasis is J n t as defined above for all integers like so. Okay, so now we're getting someplace. This now gives us a way of building up our approximation at any scale. And the way this will work is we can now build up a signal approximation at multiple scales, and it looks like this. X of t is equal to the projection onto V naught plus the projection onto W naught plus, and this is going to go on for a very long time because, as you know, in order to represent something perfectly, we have to do an infinite number of these. And so I'm just going to stop right now. But this right here is the same as the projection onto 1. So let's go back up and look at this chart. So we have the projection onto V naught, our space in the center of that diagram. The projection onto W is a projection onto that yellow space around it. So the yellow space around V naught plus V naught is going to be all of V1. So that's what we've done here. And if we take all of that and include the projection onto W1, we're now going to get everything inside the green circle, including the green circle itself. And this is the projection onto V2. Okay, so just notice one thing. That is that when we take the wavelets, the way they're labeled here, we take our wavelet at 0 and our scaling function at 0, our scaling space and our wavelet space index 0 gives us the scaling space at index 1. So the Haar wavelet system now gives us x of t is equal to so far, while I write this, I might note that so far we're dealing with continuous time signals, and most signal processing is not done with continuous time signals. What do we do about that? Well, we'll get there. We developed the theory here, and for me, when I was learning about this in graduate school, this was one of the big disconnects that I didn't understand. Managed to take a class from the math department just in wavelets. When it was all said and done, I still think I didn't perfectly understand what was going on. But I've got a much better understanding now, so hopefully I can help you pass some of the gaps excuse me, that I had in my understanding. Okay, so this first term is just a projection onto V naught. So what's going on here? This next part . Right here is the projection onto wavelet space J x of t. So the signal itself is going to be our projection onto our scaling space V0, and then the sum of all the infinite projections onto the scaling spaces. So I have one plot to show you that kind of illustrates this, and then we'll call it good for this lecture. Okay, so here we have here we go. Here we have signals at different scales. So we have our scaling function at j equals 3 in the left column. In the next column, the upper part, we have at j equals 2, kind of the broader scaling function. And then below that, we have the wavelet functions that show the difference between them. So our scaling space V3 is going to produce the finest, at least in this example, representation of a particular function. So V2 is going to produce a function that is coarser, and the difference between the coarse function in V2 and the function in V3 is spanned by this wavelet space W2, which is shown here. Then as we go to a coarser approximation, so we're now going backwards. Remember at first we looked at it going forward from very coarse to increasingly fine. So now we're going to assume that we have our really fine representation, and we're looking at coarser representations. Now this little flip is one of the tricks to understanding what's going on when we move to filter banks, looking at what's going on there. In that particular case, you might view the approximation, and this is just for intuition, it's not totally accurate, but you would view your finest approximation as your individual samples, and as you go to coarser approximations towards the right, you're getting kind of averages and differences between those samples. The averages look kind of like a low-pass filtered version, and the differences look like a high-pass filtered version. And so you take your individual samples, and now you represent it in the two spaces with a lower j number that represent high frequency content and low frequency content of those samples. So we're going to come back to this, but I'm trying to get you to view it from both angles that way. So as we go to lower and lower numbers, we get to coarser and coarser until we get to the coarsest representation that we're interested in this case, V0. And once again, at every given step, we have a scaling space and a wavelet space that are used to create the finer space out to the left. All right. That's it for today.